Hello everyone, welcome to my lecture series of electromagnetic fields. We will discuss different theories, phenomena and numerical solution of different cases in this series. I hope this series will give a fruitful outcome to physics scholars or engineering students. So, in the last part of this lecture series, we have seen three basic algebraic operations named as scaling, addition and subtraction of vectors with their properties and applications. Now, to see that content, press the I button at the top of your screen. Today, we will discuss scalar multiplication or dot product with its properties and application. So let us start. So scalar multiplication or dot product of vectors are operated when required resultant quantity is scalar. That is, the dot product of two vectors gives scalar result. The dot product is generally shown with the sign dot. So if we want to have a dot product of two vectors, let's say a bar and b bar, then its dot product is denoted by a bar dot b bar. Now it is defined as the multiplication of magnitudes of both the vectors and cosine of smaller angle between those two vectors. So how does a bar dot b bar define? So it is defined as the multiplication of magnitudes of both vectors. So magnitude of first vector, that is magnitude of A multiplied by magnitude of B, and with this multiplication we also need to multiply the cosine angle of these two vectors. So let us say theta A B. Fine. So mathematically this is how the dot product of two vectors is defined. So here for an illustration we have two vectors A and B, then we can define two angles, that is theta, and another angle between same two vectors A bar and B bar is 2 pi minus theta. Both are the angles between A bar and B bar, but in calculation of dot product we need to consider these smaller angle, that is theta. Fine. So here in place of theta AB we need to consider the smaller angle and not the greater angle. This thing should be clear in our mind. Now let us discuss some properties of dot product. So to understand all the properties, I have listed 8 different properties of dot product, and for that I have taken 3 vectors A, B and C. Fine. So let us see each property point by point. So very first property is if two vectors are parallel. So for an example, let us say I have a vector A bar in some particular direction and another vector B bar with different magnitude, but the direction is same as the direction of A bar. Then here the angle between these two vectors, that is theta AB, will be 0. So theta is 0, and that is why in this equation cos 0 will turn out to be 1. So for parallel vectors A bar and B bar, its dot product is nothing but the multiplication of their magnitudes. Secondly, if two vectors are perpendicular, so another example, if I have A bar lies on x-axis and B bar lies on y-axis, then we have 90-degree angle between A bar and B bar. So if we put 90 degree in this equation, so cos 90 will be 0, and hence whole dot product will result into 0. So if any two vectors which are perpendicular to each other, the dot product of such vectors will always be 0. Third property is law of commutation. Now law of commutation states that A bar dot B bar will be same as B bar dot A bar. So there is no difference, either you perform a dot product and perform another dot product with changing the sequence of vectors. Fine, both the results will be same. Fourth property is law of distribution. So a bar dot b bar plus c bar can be written as a bar dot b bar plus a bar dot c bar. Fine. So you can distribute the dot product among addition or subtraction of vector. Next property is the dot product of any vector with itself is the square of its own magnitude. It is also very easy to realize. So if we have a vector a bar, something like this, and if we perform a bar dot a bar, then obviously the angle between vector and itself is 0. So in this case theta will be 0. So it will be modulus of a bar cos 0. And now cos 0 is nothing but 1. So this product will result into the square of its own magnitude. So a bar dot a bar will be modulus of a bar square, because here cos theta will be 1. Now consider the base vectors of a Cartesian coordinate system, that is ax bar, ay bar and az bar. Here at this point we need to understand the meaning of base vectors. Fine. So any coordinate system can be defined as a standard coordinate system if its principal axis is making 90-degree angle with each other. So here for example I have shown you the three-dimensional Cartesian coordinate plane. So we have x, y and z direction, and all are mutually perpendicular, that is x and y is forming 90-degree angle with each other. Similarly y and z and x, all three principal directions are mutually perpendicular. Fine. So if we have any unit vector, basically base vectors are nothing but unit vectors. So if we can have a unit vector which shows the direction of its principal axis, so let us say we have a unit vector ax bar in this direction, so this shows the direction x. Similarly we can have another vector, unit vector ay bar, so this shows the direction y, and one more unit vector, let us say az bar, so it shows the direction z. So these three vectors which shows the direction of principal axis of any coordinate system are called base vectors. Fine. So unit vectors which shows the direction of principal axis. Fine. So for Cartesian coordinate system, ax bar, ay bar and az bar are called base vectors. Fine. We will discuss cylindrical coordinate system and spherical coordinate system as well. So at that time the base vectors will be changed. So all these are mutually perpendicular. That means all these principal axes are making 90-degree angle with each other. So theta xy, theta yz and theta zy all will be 90-degree, and we know that cos 90 is nothing but 0. So performing dot product with base vectors will result into 0. Fine. So any dot product with different principal axis direction will be 0. Now seventh property states that dot product of any unit vector with itself is always unity. It is also very easy to derive that if two vectors and we are performing a dot product of any unit vector with itself, then its magnitude will be always 1 and angle between x direction and x direction will be 0. So cos 0 degree. Here this magnitude will be 1 as ax is unit vector. So 1 into cos 0 again 1 will result into unity. these two property, number 6 and number 7, is very important where when we will derive any theory related to electric field or magnetic field. Eighth property, it actually shows how to calculate the dot product in Cartesian coordinate system. So here we have taken two vectors a bar and b bar, and the representation is kept as a vector form. Fine. We can represent any point. Let us say we have some point P 2, 2, 4. Fine. So if we want to represent this point P in terms of vector, then we can write OP bar, or sometimes people only write P bar, that is point which we want to represent. So its x coordinate px and direction of x, which is represented by ax bar, plus its y coordinate and direction of y, plus its z coordinate and direction of z. Fine. So this point P224 can also be written in a vector form as 2ax bar plus 2ay bar plus 4az bar. Fine. So both these representations are correct. Fine. This form is vectorial representation of point, and this is a point representation. So if we have two vectors a bar and b bar with its coordinate and principal axis direction, then a bar dot b bar can be determined by the multiplication of both vectors x component, the multiplication plus the multiplication of y component of both vectors plus multiplication of z component of both the vectors. Now this equation is also very easy to derive. So let us derive that. How does it come? So for that we are taking vector a equals to x coordinate and direction of x plus y coordinate of a, y direction, plus z coordinate of a and z direction. Similarly, vector b can be written as x coordinate of b. Now direction of x can only be shown by ax bar. Fine, because these unit vectors only shows the direction. So here we need not to write bx bar. Fine, because it has the same meaning. So plus y coordinate of b, direction of y, and z coordinate of b with the direction z. Now if we take dot product, then we know that dot product is only be applicable to with vectors. Fine. So here we will multiply each term of a bar with all the terms of b bar with the sign. Fine. So if we multiply ax into ax bar with b bar, then it will be ax bx. These two are scalars, so dot product will not be applicable on these, rather it will be applicable on the unit vector. So ax bar dot ax bar. Fine. Plus multiplying with this term, so it will result in ax by. Dot product will be applicable to unit vectors ax bar dot ay bar plus ax bz, ax bar dot az bar. Fine. So we have done multiplying first term of a bar with all three terms of b bar. Now we will take second term. So it will result in ay bx, ay bar dot ax bar plus ay by, ay bar dot ay bar plus ay bz, ay bar dot az bar. Now multiplying the last term, it will result in az bx, az bar dot ax bar plus az by, az bar dot ay bar plus az bz, az bar dot az bar. Fine. Now, recalling the property number 6 and 7, we know that the dot product of any unit vector with itself will result into unity. So this dot product will result into unity. Same way, this dot product and the last term dot product will result into unity. And we have also a property in which we have seen that the dot product of mutually perpendicular unit vectors will be 0. So these 6 terms, that is ax bar dot ay bar will be 0, ax bar dot az bar will be 0, same way ay bar dot ax bar, ay bar dot az bar dot ax bar and az bar dot ay bar, all these terms will be 0. So finally we will only have ax bx plus ay by plus az bz. So this is how we can prove that the dot product of two vectors in Cartesian coordinate system can be determined with summing the x, y and z coordinates, the product of x, y and z coordinates of both the vector. Fine. So basically we have two equations as far now. So a bar dot b bar we can directly calculate by its coordinates if it is known. Otherwise we can also find a bar dot b bar with this equation which is derived by the definition of the dot product. So these two are the important equations which can be utilized while we will solve the numericals. Okay, moving further, now we will see the application of dot products. So its first application is to determine the angle between two vectors. Now it is very easy to visualize that if I am writing a bar dot b bar equals to modulus of a bar modulus of b bar cos theta, then this theta is nothing but the angle between a and b. So if I want to find the angle between these two vectors a and b, then I will make cos theta as a subject of this equation, and my equation will turn out to be a bar dot b bar divided by modulus of a bar modulus of b bar. Now again, if this cos function goes to right hand side of the equation, it will be cos inverse a bar dot b bar divided by modulus of a bar modulus of b bar. Fine. So this is how we can find the angle between two vectors with the help of dot product. The second application is to find the component of any vector in given direction. So for the understanding of this application, let us say I have a reference direction r and some vector p which is making angle theta with the reference direction. Fine. So if I want to find the component of p in the direction of r, so that is nothing but this length of line on the reference direction. Fine. So value of this component, fine, it is called as projection of p on r. Fine. It can be found as, so we simply need to take a dot product of that vector with the direction we are interested. So if we find p bar dot a bar, then it will nothing be but modulus of p bar modulus of ar bar and cos theta, because the angle between p bar and direction is theta. Now magnitude of unit vector will be 1, so we will have modulus of p bar cos theta. So this will be the length of the projection of p on the direction of r. Fine. If we want to show this in a vector form, then we can write it as, in a vector form, let us say projection of p on the direction of r. So in vector form it can be written as modulus of p bar cos theta ar bar. Okay. So this is the second application of dot product. We can find the projection or any component of vector in given direction. And the third thing is to determine the work done by any force. So it is very well known formula from physics that work done W is nothing but F bar dot D bar. So F bar modulus of F bar modulus of D bar cos theta. Here F represents the force and D represents the displacement. We can also find many other applications, fine, but here for the understanding of you guys, I have only taken 3 applications. So the equations for each applications is also shown here, fine. In next video lecture, we will discuss the cross product or vector multiplication. One more thing that I want to show you is that in classical mathematics, when we are having a two-dimensional Cartesian coordinate system, so only x and y axis will be there. At that time, we always seen that x component is defined as cos theta. Let us say the length of this line is capital L, then this component will be L cos theta and this component will be L sin theta. So this fundamental understanding of geometry can be satisfied or can be proved with the help of dot product. Okay, now let us say if we have theta angle with reference to x axis, so we can say that we have pi by 2 minus theta angle with respect to y axis. Fine. Here one more geometrical formula can be determined. Fine. So if this angle is pi by 2 minus theta, then this component is nothing but L dot ay bar, and L dot ay bar will turn out to be L modulus of ay bar cos pi by 2 minus theta. So it will be L modulus of ay bar will be 1 and cos pi by 2 minus theta will be sin theta. So this is how we can judge that if x component is L cos theta, then y component will be L sin theta. Ultimately, it is the reference axis with respect to the which we are taking the angle is important. So that's it for today. Thank you very much.